Ever wonder how something so small can be so powerful? I'm talking about bullets. Those sleek little projectiles that somehow manage to fly hundreds of meters, punch through steel, and land with the kind of precision that makes even seasoned engineers go, how the heck did they build that? We see them in movies all the time, spraying from helicopters, zipping through windows, spinning dramatically in slow-mo. But unless you're in the military, law enforcement, or a seasoned hunter, you've probably never stopped to ask, where do bullets come from? Who makes them? What kind of engineering insanity goes into creating something that deadly, that fast, and that reliable? Because here's the thing, bullets aren't just hunks of metal. They're the result of centuries, and I mean centuries, of warfare, chemistry, physics, and frankly a bit of genius. From molten lead and spinning copper to precision crimping and military-grade testing, we're breaking down every step in the journey from raw material to high-velocity marvel. Let's rewind the clock. And I don't mean a few decades, I mean all the way back, like before smartphones, before cars, before indoor plumbing. We're going to 9th century China, where an ambitious alchemist was probably in his workshop mixing weird powders in the hopes of becoming immortal, or at least curing a cold, and accidentally kicked off a global arms race. That's right, gunpowder. A happy little accident that turned out to be the single most disruptive invention in the history of warfare. One moment, they were trying to find the elixir of life, and the next, boom, literally. Black powder, made from saltpeter, sulfur, and charcoal, was born. And suddenly, people weren't just throwing spears anymore. They were launching explosions out of bamboo tubes. It didn't take long for word to spread. By the time it reached the Middle East and Europe, gunpowder had evolved from firecrackers to cannons the size of wagons. Kings started replacing knights with gunners. Castles once thought impenetrable were suddenly getting blown wide open. Warfare had changed. Forever. Fast forward a few hundred years to the 16th and 17th centuries, and you've got these early firearms called muskets. They were big, clunky, and you had to stand there like a medieval barista, pouring in powder, stuffing in wadding, and then dropping in your bullet, which, let's be real, wasn't really a bullet yet. It was more like a lead marble. A spherical lump. No grooves, no finesse, just a ball of metal praying it hit something other than the dirt. Imagine trying to shoot with one of those. You pull the trigger, and half the time it misfires. The other half? The ball veers off like it's got a grudge against accuracy. These things were loud, smoky, and terrifying, but not always effective. Still, they were enough to make people rethink the whole swords and shields thing. And then came the mini ball in the 1800s. Now this was a game changer. Designed by a French army officer named Claude-Étienne Minié, this wasn't a ball at all. It was a conical-shaped bullet with grooves at the base. When fired, the hot gases would expand the base into the rifling grooves of the barrel, spinning the bullet for a much more stable and accurate flight path. That little spin? It's the same principle behind a football spiral or a well-thrown curveball. It gives the projectile stability. Suddenly, shooting wasn't just about spraying and praying. It was calculated, deadly, efficient. Once that door opened, the bullet's evolution went into overdrive. We started experimenting with jackets, grooves, pointed tips, and different metals. By the late 1800s, the traditional spherical bullet was history. Bullets got longer, slimmer, faster. Chemistry made the propellants more powerful. Engineering made the casing stronger. By the early 1900s, bullets had transformed into the sleek, brass-tipped projectiles we see today. And here's the crazy part. Even after all that innovation, we're still tinkering. Modern bullet designs continue to be refined for different purposes: hunting, target shooting, law enforcement, and of course, military applications. So now that we've time traveled through over 1,000 years of weaponized innovation, let's zoom in and figure out how a modern bullet is actually made. And I'm not just talking about the final product sitting in a magazine. We're starting way before that, at the raw, gritty, industrial level. This is where the magic begins. The first star of our show is lead. Heavy, soft, and weirdly dependable. Think of it as the muscle of the bullet. Lead has been the go-to material for cores for centuries, and there's a reason for that. It's super dense, which means it packs a serious punch in a small size. And because it's so soft, it deforms on impact, creating more internal damage in soft targets. If you've ever seen those slow-motion videos of hollow points mushrooming on contact, yeah, that's lead doing its thing. Next up is copper, the classy, polished partner to lead's brute force. Copper's job is to wrap the lead core in a shiny aerodynamic jacket. Not only does this make the bullet fly smoother and straighter, but it also protects the lead from melting or smearing inside the gun barrel. Copper is tough enough to handle friction, but soft enough to mold. Think of it as the perfect wingman. Keeps things clean, smooth, and on course. Now sometimes copper and lead aren't enough. Enter steel and tungsten, the heavy-duty specialists. These are used in rounds that need to punch through armor, barriers, or even light vehicles. Steel is cheap and strong, great for mass-produced military rounds. But if you want something even denser, something that hits like a meteor, you go with tungsten. This metal is so heavy that a tiny tungsten core can weigh as much as a full-size lead one, and when you send it flying at high speed, it does not stop. Each of these materials has a specific role. It's not just about making something that looks cool, it's about making something that works. Works under pressure, under stress, in heat, in cold, through wind, rain, mud, everything. Because a bullet doesn't just sit on a shelf. Once it's fired, it goes from 0 to 3,000 feet per second in a blink. It spins thousands of times per second. It experiences crushing pressure and blistering heat. Every part of it has to be engineered for chaos. And we haven't even talked about the rest of the round. The propellant, the primer, the casing, all of which are about to join this wild ride. So yeah, bullets might be small, but behind that tiny piece of metal is a story that's over 1,000 years in the making. And trust me, we're just getting started. Now if we're talking armor-piercing rounds, forget everything soft and squishy. We're stepping into the world of heavy metal hitters, the ones that don't knock politely, they bulldoze through. This is where steel and tungsten come strutting in like heavyweight champions. Steel, for starters, is already a step up from lead. It's tough, durable, and way less prone to deformation. It holds its shape like a champ, which is exactly what you want when your goal is to penetrate armor rather than just splatter on impact. Imagine trying to stab a watermelon with a spoon versus a chisel. That's the kind of difference we're talking about. Steel doesn't just deliver a punch, it concentrates force into a fine, unforgiving point. It's strong, reliable, and cheaper than the exotic metals, which is why it's often used in military surplus rounds or training ammunition that still needs to hit hard. But when things get serious, like we need to go through an engine block, serious. Steel steps aside, and tungsten takes the stage. Tungsten is one of the densest natural elements on Earth. This stuff is so heavy, if you drop a chunk of it in your hand, your wrist might start filing a complaint. And that density is its superpower. In armor-piercing rounds, a tungsten core acts like a battering ram wrapped inside a bullet. It doesn't flatten, it doesn't bend, it just barrels forward, like it's angry at the entire periodic table. In fact, tungsten is so effective at penetrating armor that it's used in some of the world's most advanced military munitions. Anti-tank rounds, aircraft cannon shells, even space-bound satellite shielding. If it can survive re-entry from orbit and still punch through steel plating, yeah, you want it in your bullet if the goal is to defeat armor. The manufacturing process for these armor-piercing cores is also dialed in with surgical precision. Tungsten isn't just slapped into a mold and called a day. It's machined, carefully shaved, cut, and shaped into dense little cores that fit perfectly inside the bullet jacket. Everything about them is engineered for one thing: penetration. Not expansion, not fragmentation, just straight up brute force through whatever's in the way. And get this, because these rounds are so effective at what they do, they're often regulated by law. Civilians can't just go buy tungsten core rounds off the shelf in most countries. These are professional grade tools, often reserved for military and law enforcement use only. But whether it's a hardened steel tip or a tungsten penetrator, the purpose is the same: deliver maximum energy, pierce through barriers, and keep going like a wrecking ball on a mission. It's engineering meets physics meets raw elemental power, all packed into something small enough to sit in the palm of your hand. So next time you see an armor-piercing round, just know you're not looking at just a bullet. You're looking at a specially crafted missile, forged from the hardest materials on the planet, built with one goal in mind: go through. Not around, not over, through. But it's not just about the projectile itself. We also need the boom, the thing that makes it all go flying. That's where propellants come into play. Modern gunpowder isn't actually powder anymore. It's more like a fine granular mix of nitrocellulose, sometimes with nitroglycerin for an extra punch. This stuff burns fast, like blink and it's gone fast. But it burns in a controlled way, generating a burst of hot gas that forces the bullet out of the casing and down the barrel. And don't forget the primer, that little cap at the base of the casing. It might look insignificant, but it's the key to everything. The primer contains a shock-sensitive explosive that ignites when struck by a firing pin. That tiny explosion lights up the main powder charge, and boom, you've got a bullet in motion. Now that we've got our ingredients, it's time to get messy. Step 1, processing the lead. This starts with big chunks of raw lead being melted down in industrial furnaces until they look like bubbling gray lava. Then the molten lead is cast into ingots, those familiar rectangular bricks, and cooled. Once solid, the ingots are either extruded into long, thick wires or chopped and molded directly into the shapes needed for specific bullet calibers. These shapes aren't random. Engineers spend years testing different nose profiles, lengths, and weights. Why? Because even a half-millimeter change can affect how a bullet spins, how fast it flies, or how it behaves on impact. While lead is doing its thing, copper is being rolled into ultra-thin sheets. These are stamped into small circular blanks, which are then pressed into cups, the beginnings of that famous copper jacket. Depending on the design, the jacket might cover just the bullet's base or its entire body. This layer protects the lead core during the violent journey through a gun barrel, and it also gives the bullet aerodynamic stability in high-tech rounds, especially armor-piercing or military-grade. We start to see steel cores or tungsten rods being milled with CNC precision. Every tiny cut, angle, and curve is deliberate. You're not just machining metal, you're shaping the very physics of impact. Meanwhile, back in the chemistry lab, it's time to make the magic powder. Raw nitrocellulose is treated, dried, and mixed into grains that look like tiny dark flakes. This process happens in super controlled environments because, yeah, it's flammable. You don't want your assembly line going kaboom before anything even gets loaded. The primer mix, by contrast, is usually made in small quantities in isolated bunkers. We're talking ingredients like lead styphnate, barium nitrate, and antimony sulfide, all of which are highly reactive. These are pressed into minuscule cups and sealed until they're ready to be installed at the very base of the casing. And now, it's showtime. The assembly line is where it all comes together. First, the lead core is inserted into the copper jacket. Machines press them together with the kind of precision you'd expect from a space program. Then the bullet is formed, sometimes with a sharp tip, sometimes with a hollow point, sometimes boat-tailed for long-range aerodynamics. Every feature has a purpose. Next comes the cartridge casing, usually made of brass, though steel or aluminum can make appearances. The primer is pressed into the base, followed by an exact measurement of propellant. Too little powder, and the bullet underperforms. Too much, and you're basically holding a tiny pipe bomb. It's all calculated to microgram precision. Finally, the bullet is seated into the top of the casing. The machine applies just enough pressure to lock it in. Then comes crimping, a mechanical process that curls the lip of the casing inward, locking the bullet in place. And just when you think it's ready to ship, nope. Testing is up next. Random samples from each batch are weighed, measured, and microscopically inspected. They're fired down specialized test barrels, tracked with high-speed cameras and radar sensors. Lab techs analyze the groupings, muzzle velocity, recoil, barrel pressure, you name it. If even one metric is off, the whole batch could be scrapped. Quality control in ammunition manufacturing is no joke. People's lives literally depend on it. Only after all that do we get to packaging. Bullets are sorted by caliber, load type, and purpose, then packed into heavy-duty boxes labeled with enough info to satisfy a NATO general. From there, they head out to gun shops, police departments, military depots, and training grounds around the world. And yet, the process doesn't stop evolving. Bullet tech keeps advancing. Today, we have tracer rounds that light up like fiery comets, smart bullets with microchips, and subsonic ammo designed to whisper instead of roar. But even the simplest bullet is a marvel, a blend of metallurgy, chemistry, physics, and pure mechanical genius. Next time you see one on a movie screen or at a range, remember, that tiny object took dozens of steps, dozens of machines, and the minds of countless engineers to create. That's the real secret behind bullet production. It's not just the bang, it's the brains.